This is an algebra video about modular functions. And over the course of the video, we're going to be looking at features of modular functions, graphing modular functions, and how to sketch modular functions. So a modular function might look like something like this. I know it's a modular function because I've got the absolute value lines either side of the function. Remember that the absolute value lines mean that no matter what values I put in for x, I take the overall positive version of x plus 1 as my result. Since I make sure that all my results are positive, it means that the function f of x must always be positive, although it is permitted to touch the x-axis. So we can say that f of x is greater than or equals to 0. And the modular function of this type will appear above the x-axis. Let's have a look at how to graph a modular function. So the question looks like a regular graphing question. Graph f of x equals to the absolute value of x plus 1 in the domain minus 4 up as far as 2. So that means I want to take x values starting at negative 4 up as far as positive 2 and work out my result for f of x in each case. And I'm going to make a table out to evaluate my f of x values. I'm going to go through a number of steps to get from x to f of x. So I'll have my row for x values, then I'll work out x plus 1, and then I'll find the absolute value of x plus 1. Since I've been instructed to go from negative 4 to 2, I will list those values out in the x row. And then in the next row, I'm taking each x value and adding 1 to it. Finally, I have to take the absolute value of each value in the x plus 1 row to get the absolute value of x plus 1. And these are my f of x values. Before we proceed any further, let's just take a moment to recognize how like the way we'd go about graphing the function of a line this process is. If I was graphing the line x plus 1, I would just have these two rows, and these will be my points. If I was graphing a line, it would be permissible to go into the negative values for f of x, and so I'd be able to go below the x-axis. However, in the case of the modular function, because I've got absolute value lines in my function, I'm only going to be dealing with positive outcomes, which will mean that I'm going to be located above the x-axis. So now let's draw the graph to go with the table. So I've drawn my x and y axes, and then the points that I'm going to mark in will be minus 4, 3, minus 3, 2, minus 2, 1, minus 1, 0. It's tempting to continue on down in a straight line below the x-axis, but actually I'm going to bounce right back up again to 0, 1, 1, 2, and 2, 3. Connecting these points gives me my graph of my function f of x equals to the absolute value of x plus 1. And we can see that we end up with a V-shaped graph. The graph touches the x-axis, but does not go below it. The graph is also symmetrical, and the line of symmetry is a vertical line through the X intercept. Speaking of intercepts, the modular function has an X intercept and a Y-intercept, and these can be useful references when sketching a modular function, and we'll look at those in a moment. Graphing requires a degree of accuracy, where I work out multiple points and use those to get an accurate image of what the diagram of the function should look like. Sketching should give us an idea of the appearance of the function with a little less detail than graphing. However, we'd like to know key pieces of information about the function. One of these key pieces of information is the position of the X-intercept. Now that's where the function meets the x-axis. We know that the x-axis can be viewed as y equals to 0. In this case, g of x is the same thing as y. And since g of x is the absolute value of 2x plus 4, then to find the x-intercept, I should allow this equals to 0. Now, I could, if I wanted to at this stage, square both sides of that equation, and I could multiply that out and get a quadratic on the left-hand side. You can do that now yourself if you like. And then I'd have to factorize that quadratic, and I'd have to solve. But if I stop at this point and have a think about what would happen when I multiplied my quadratic out and then factorized it again, do you have any idea at this stage what those factors might look like? Well, since I'm squaring 2x plus 4, the factors would be 2x plus 4 by 2x plus 4. I have a perfect square, so the two factors are the same, so I'll only get one solution for this. Effectively, I'll be letting 2x plus 4 equals to 0 and then solving for x. So my x-intercept is x equals minus 2. The other key point that I'd like to find is the Y-intercept, or where the function goes through the y-axis. To figure this out, I'd need to let x equals to 0. So I go back to my function, I insert 0 for x, and I evaluate the result. This just gives me the absolute value of 4, which of course is 4. I've written this as y equals 4. If you like, you'd call it gx equals 4. At this point, I'm going to draw my sketch. I've drawn my x and y axes, and I can mark in the 2 points that I've worked out, the x-intercept and the y-intercept. I'm then going to join those 2 points together, but be careful, I'm not going to go beyond either of them for the moment. I now have the beginnings of the sketch of my function, but it's not complete yet. I know that I should have a v-shaped function that is entirely positive. I also know that I should have an axis of symmetry as a vertical line going through the x-intercept. So to complete my function, I must simply reflect the portion of the graph that I've sketched so far in that axis of symmetry and continue to the left here above the x-axis. And I'll try and be as accurate as I can. I can see that I'd have to go -1, -2, that's 2 spaces to get from my y-intercept across to the line of symmetry. So I'm going to go 2 more spaces on the far side in order to complete my sketch. And finally, a couple of things to note from the graph and the sketch. If I think of a modular function being in the form absolute value ax plus c, then the x-intercept can be written as minus c over a. The line of symmetry can be written as x equals minus c over a. And the y-intercept can be written as the absolute value of c.